today my presentation will be more on the non-destructive testing side. So, and I'll also give you an overview of course, composite structures. Vishwanathan sir has given a very good presentation on the construction part. So I'll be talking more on the destruction part, or rather the testing part, destructive testing part. So here we go. So I'll skip the intro. I know I'm in middle of lunch and you guys, so I'll just skip the overall what is composite structure and the other things, so that we come straight away to the topic. So basically, when we talk of any kind of structures, these are the ultrasonic testing, then radiography, impact echo testing, ground penetrating radar, load testing, visual inspection, acoustic emission testing. These are the available tests that are there. When we go to a little more advanced technology, these kind of structures, basically when we talk of construction wherein a composite structure construction, it is very difficult after construction to see what is inside, like whether concrete is done properly or not. It is very difficult to analyze that. So for that, there are many advanced technologies like integrated structural health monitoring system. I'll go into each detail of each of the topics. Then use of fiber optic technology, wireless and IoT based monitoring systems, digital twin integration, that's also a very important thing in this kind of construction, AI and machine learning in data analysis, monitoring during construction and post construction, code and compliance driven systems, retrofitting of old structure with monitoring systems, and drones and robotic for external inspection. So this sums up the entire system wherein you can actually test and monitor a structure during and after construction. So if you talk of integrated structural health monitoring system, it comprises of sensor network with strain gauges, accelerometers, fiber optic sensors, corrosion sensors, half cell potential sensors, temperature and humidity sensors, and smart tube constructions. So that is all the the sensors are installed in the tube itself. So after construction, you get a complete information about the entire system of concrete and overall structural behavior, composite behavior of the structural. Similarly, use of fiber optic technology. So distributed fiber optic sensing is also one way of doing it. It is now used in concrete lining also. Even in some places we have seen it used in top layers of gunneting or even the jackets or other things they are used. And there are many types, like DTS is for temperature, then strain, even acoustic is there. So there are various types, and the benefit is they are very accurate and they are very it gives you the perfect information about the overall behavior of the structure. Similarly, wireless and IoT based monitoring system. I will also take one case study for that as well. AI, of course, with every case you do or every information you have, you can upgrade. We'll show you how we have, in one of the case, how we have, did some regression analysis, and by having data, how we could correlate or rather come up on a perfect solution wherein we had variation in results, how we could zero in on that. And finally, monitoring during construction and post construction, which is of course a very appropriate method to do right now. So we'll take, I'm going to, rather I'm not just focusing on buildings, but we'll take different kind of structures. So you have a overview of all kind of structures and what we did in that specific structure and why we did what we did there. So this is a coke oven plant wherein there was some problem in the boiler, and as a result they had to they can't shut the boiler, but there was some problem in the boiler and they had to divert the flow in the chimney. This is the chimney here. Now the shutdown went on for almost 2 months, and this chimney was not designed for elevated temperature for prolonged period, and as a result just the lining just above the duct on both sides started collapsing, and when the lining collapsed, the concrete was subjected to 800 degrees of Celsius of temperature, concrete caved in, after that steel melted and the chimney started buckling. Now you cannot stop the plant, because if you stop the plant, the coke oven bricks which are there, if they go below the temperature of 750 degrees, the bricks will crack. And naturally, you'll have to revamp the entire plant. That is not possible. You can't push the flow in the boiler because boiler is shut down. If there is a flow in the boiler, there will be a blast in the boiler. So the only possible thing is to keep the chimney running. Now there was a potential risk that the chimney had buckled by almost 2 inches, and if it further goes, the chimney may collapse, and it's a almost 80-90 meter tall chimney. What can be done? So that is the time we were roped in. We saw the structure. So I'll just give you brief of what all we did and what solutions we provide and how we monitored that for about 1.5 years till the new chimney was built, right? So that's the crux. So this was the condition, and this was just at 15 meter height, and you have almost 65-70 meter of structure standing on that. You can see inside out. I mean, this was the. So, what we did was, internally there was an endoscopy done just to see what is the extent of damage. So when we saw that, we realized that the extent was only limited to 2 meters in height and only 40% in periphery. So 60% was still intact. So what we did was, and you can see the condition of the concrete also here. Sorry, just a back. You can see the condition of concrete and steel. It has melted. There is nothing left. So what we did was, we started taking temperature, because every day we can't do endoscopy. So what we did was, on the shell outside, about 7.5 meter on both sides, we started taking temperature on a regular basis, so that we know if that is any further lining collapse, the temperature in that portion will elevate, and we'll know that okay, the lining is stabilized or it is still collapsing. To our luck, the lining after that collapse was stabilized. And what we did was, the client said that, can we patch up this with some refractory mortar or something? We said, don't do that. It's like a pressure cooker. You have to allow the hot air to vent out and not allow it to cook inside. So what we did was, we allowed it to vent out, and that step probably helped us. We started taking temperature, so we could see only at a couple of points there was elevated temperature, rest was all okay. These are some design calculations we did. So what we did was, imagine you break your leg and doctor fix that with a steel rod, right? They provide an entire cage and they fix your bone top and bottom. So probably we copied that from them. So we said, if we can design a cage and connect the top and the bottom portion, we are done. And because the shape of the chimney is inclined, that cage will not slip down. That was for sure, right? Because of the mere shape of the wedging action will be there. So what we did was, we designed a steel cage around the system and made sure that it takes care of the 40% of the load, and erected it on site. What precautions we took, what sensors we used to monitor that, I'll show you that. I'll go into the detail of that. So initially what we did was, we did a complete GPR survey. GPR stands for ground penetrating radar. That helps you detect the steel and the cover portion. Because in this process, we were using almost 4,500 anchors to stick this frame to the concrete. So we wanted to make sure that we don't puncture any of the steel. None of the reinforcement should be punctured, because we already, short of reinforcement in that span. So we didn't want it to make it worse. So every plate, every base plate was made, the anchors were fixed on the site, templates were cut, they were checked on the site, and then the base plate was prepared. That's how it went. Then we also did some, we did 3D scanning to understand, because this structure was not straight and construction, errors also were there. Apart from that, there were bulging. So we wanted to make sure whatever sections we select, whatever sections shape we give, should stick to the surface. Otherwise, if you see there is bulging here, and if I stick my section here, there will be a gap in between this. And when you create gap, my capacity of the member reduces because it is moving away from the structure, not to the, not close to the structure. So later on, you can see every base plate, every member is numbered. So this is the structural system that we built around this, and the damage was at this portion. And later on, we had installed all kind of sensors. Like initially, we had sensors for temperature, we had sensors for wind, we had sensors for we had some strain gauges fixed to that, we had deflectometers, inclinometers. So what we did was entire thing was connected to a system, wireless based system, wherein we used to get reading, regular reading, and we had set a threshold limit. So whatever the whatever the design was there, we set a threshold limit at 33%. So if it goes beyond 33%, supposing if my deflection is permissible is maybe 80 mm, we set it at 30% of that 80 mm, 33%. So that what happens is if it goes beyond that, at least we know that we have to vacate that place. We couldn't have done much after the structure is, if it had to fall. So we had told the client that it is a stopgap arrangement, and if things worsen, probably the last thing would be you will have to stop the plant. So they had agreed on that, and we observed this structure through sensors. Everything was connected through sensors. You can see the strain gauges also were there. Everything was, sensors were fixed to certain locations. We had the overall threshold limits also set. We had the limits also set. So based on this, the entire networking was done, and we were getting readings. So if there was only once we got an alarm, there was a heavy wind gust, and only at that time the deflection crossed that limit, but luckily it came back. So we were safe in that condition, and also the fact that we were convinced that the whatever system is there, it is working properly. So this is the complete networking of cabling to the entire sensors which was done, and that was taken to a complete control center, data logger. And from there, we were wirelessly getting the data on our emails, phone numbers, everywhere. And this is the overall structural element, and it's been almost 2 years now, and this system is working. So client, instead of building a new chimney, said, now this is working well, so can we retrofit this in a different way? So now we are working whether we can do something on the online chimney and retrofit that much part, so that it can, and functionally it is, in all parameters it is even performed much better than what it was designed. Yes. So any questions in this, or should we move to the another one? So as we are talking of steel structures, of course it's not a high rise, but then we thought I should be talking more on steel. So this is a very good case of retrofitting of pipelines and other structures, steel structures. So we've seen retrofitting in concrete structures a lot, but what about the pipelines and other things in some petrochemical plants or plants where you can't take a shutdown, nor you can do any kind of hot work? Yeah, it's very difficult to change the pipeline. Like in petrochemical plants, if you tell me that I have to, pipes are corroded and I want to change the pipes, you'll not be able to take shutdown, because each day of shutdown costs hundreds of crores. And secondly, you are not allowed to do any kind of hot work, not even grinding is permitted, right? So this is the case wherein in a petrochemical plant, a refinery rather, this was the complete pipeline, and the pipelines were corroding, almost 20-year-old pipelines. They were corroding, they were leaking, and lot of, what they were doing was they were using rubber gaskets with brackets to strengthen that, but they can't go on for another 20 years with this kind of infrastructure. So what was done here was, we were given this case that, okay, this is the condition. Can you repair this pipeline online? And we use composite material Like we use glass and carbon fiber here to strengthen the pipeline. The code which we followed was ASME PCC 2 2015, that is repair of pressure equipments and piping. And what, this thing, what is very important is that whenever you use any kind of composite, you have to be very careful in using that. Reason being, major issue is in the resin part, right? The binder, the matrix. Fiber are almost inert, but the resin, it will react to certain environment. Like if you have a corrosive environment of acid, or if you have chlorides, if you have different kind of environment or different temperatures, resin will react in a different way. So you have to make sure that you have to design your resin as per your requirement. I'll show you 3 different case studies of different resins being used and why we use certain resins. So these are the design parameters, and based on that, we have designed the complete system. So this was the condition of the pipeline, and this is blow down hydrocarbon. So we were not even allowed to remove the paint. No grinding was permitted. So what we did was, whatever the loose scales were there, we removed. Rest, we use a corrosion inhibiting primer here, which is very important for that structure. And later on, all the saddle supports which were there, we turned it, we used micro concrete to make it square so that there's no angle or sharp angles which we can miss in, wrapping or something. And later on, we coated this with a epoxy, not exactly epoxy, but a modified epoxy putty, so that we get a smooth surface for wrapping. It was not, see, what we designed was a standalone system. So if you remove the pipeline from inside, our pipe will work as a brand new pipeline. But what we wanted was a good base. And why we wanted this was because when the pipeline is there, and if there is any air gap in between, there are chances, because some of these are cathodically charged pipelines, so there are chances of conductivity, and there will be spark and there can be fire. So we apply first layer of this, and then secondly, first we coat it with glass. Why we don't use carbon directly is because glass is an insulating material, carbon is a conducting material. And that is why we went for initially 1 layer of glass. After this, we had a complete holiday test on this. So holiday test is you pass a spiral ring through that, and there should be no current transfer. It should be 100% holiday free surface. And then only you go for multiple layer of carbons as per the design and orientation. So these are various number of layers. And then you coat it with an entire PU paint or something. And this we have guaranteed a service life of 20 years. With just top coat of maintenance, every 4 or 5 years you have to go for PU coat. And now what we have done is, we have introduced UV resistant resins. So you don't even need to offer a top coat for this. You can go on for 20 years without that. Or maybe, and if there is any issue, you can patch repair this, and these are standalone design. I mean, even if you remove the pipeline from inside, this is good enough to take the load. Okay. So when we did this, next question we were given is that we have a heat exchanger tube which is damaged. Can we do it? The challenge here is the temperature. So the resins which we used in that were only resistant to 120 degrees Celsius. Whereas here, the resins we developed were up to 260 degrees. So the family of the resin was changed, and similarly this heat exchanger tube also was repaired in record time of 7 days during their shutdown, annual shutdown. Otherwise, to change this entire thing would have taken them at least 1.5 months. Then for another plant, fertilizer plant, they had these acid tanks. So we were given the challenge, can you retrofit our acid tanks? Because as you've done some work in steel. So that also we did. And this was just, this is not a standalone thing. This is, we've just taken care of the corrosion part. So if this section has reduced from maybe 12 mm to 6 mm, considering 3 mm as the corrosion tolerance, we've just retrofitted for that balance 3 or 4 mm, not the entire tank. We've not done a standalone tank. It will be too expensive. But yeah, the cost of changing this tank was coming to, 2 tanks we did. The cost of changing this tank was coming to 42 crores. The shutdown time required was 3.5 months. Each day costing them about 21 crores per day of shutdown. And we could retrofit this tank in their annual shutdown of 15 days and with a cost of 8 crore rupees. That's it. So, I mean, there is endless possibility. I mean, we as civil engineers should not restrict ourselves to only concrete structures. There are many things beyond, conventional structures we can work on, and the scope is tremendous. There's endless possibilities. I'm taking this case study also. I mean, I'm showing another, a structure wherein some piles were there. There are steel piles and embedded with concrete inside. So this steel is basically a sacrificial core, just to make sure that the construction happens. So that is the steel casing which is there. But similar, why I'm showing you this is because it's almost similar to the composite construction. You don't know what's happening inside the concrete, right? So this is why I'm taking this case study. So this being offshore structure, we have to take care about the scaffolding and the safety of the people. So the scaffolding is hung from top, not from bottom to top. And sir, by seeing this scaffolding, sir, I can understand what kind of a pain you must have taken from hanging the structure. We could have not hang few pipes, so I understand what kind of planning or design must have been required. So these are some of the very simple tests. So what we did here was, we removed some part of the lining which was already damaged and performed some tests like hammer test, UPV, tomography also we did. So tomography, for those who don't know, is a advanced version of UPV. It has 24 channels, and what it does is it creates a complete slice-like image. So you'll be able to see inside the concrete where exactly your defects are. Then we also did GPR, because often what happens is this kind of structure is the cover which is provided is almost 75 mm, but sometimes your mass shifts, leaving more cover on one side and less on the other side. So that also creates some issues. So we also made sure that whether everything is in line, or is there any eccentricity in the structure also. Then core extraction was done, steel thickness testing was done, corrosion testing was also done, half cell potential and other things. And this was the overall zones that we divided, what was getting damaged. So we realized that the splash zone was the zone which got more damage, but surprisingly, because this is in Dahej, and there the tidal variation is almost 9 to 10 meters, and also the wave velocity is very high. So we could see a lot of erosion below water, because there will be no corrosion below water because there is no free oxygen, but we saw a lot of erosion happening in the pile, to the extent that some places 1.4 meter of pile just was left with 200 mm of core inside. Rest was all eaten up. And surprisingly, the steel casing was also intact. Only few holes were there. So sand erosion can damage your concrete very badly. And when we did some testing, underwater testing, so what we did was, we physically checked by tapping. So some places we could see hollow sound, and some places we could see holes. So that is where we initially did some endoscopy through those holes. And when we found there was large gaps in that concrete, we removed the steel by cutting it, underwater cutting, and we found these damages. Now how do you repair those? So for that, we have evolved with a technique of pile encapsulation, which can happen underwater with divers. I'll show you the technique. This was the condition of the repaired members. So this jetty was regularly repaired. Every 2-3 years they used to repair, and the damages used to come again. You can see the condition of the repair here. These are all repaired portions. The problem was, they were not treating corrosion properly. They were only layering it by high strength microconcrete, high strength mortars, and corrosion was not treated properly. Of course, this not being the subject today, I will not go into much of detail of that. I'll just show you what we did there. And this was the condition of the repaired members. You can see there's no bond between the old and the new. New steel has corroded like this. The new steel after the pile was repaired. Brackets also same thing. Slabs also same thing. You can see all the members prematurely failed within 2 or 3 years. I'll straight away so this is the technique we adopted. This is the encapsulation technique. So what you do is, there are fiber jackets, you take those jackets. After you remove the pile liner from inside, just fix this jacket, rivet that jackets, and through a high pressure pumping system, you pump epoxy. There are epoxy resins, underwater epoxy resins. You pump through it's like a paste. So you pump through bottom to top. You see, top to bottom, what will happen is, there will be a lot of voids or water will be there. So there will be bubbling happening and it will not grout properly. So what we did was, from bottom we started injecting, and that displaced the water, and it was done at a very high pressure. Almost 5,400 bar pressure was used in the pump. And that was pumped, the liquid was pumped in the jacket, and this is how the complete retrofitting of this pile was done. Similarly, you can see how the concrete structures are there. There was some fiber wrapping also done in this structure. So this is the technique we had. So these are some of the spacers also. So what happens, why we need spacers in this is because this jacket has to be there should be a 10 mm gap around the concrete, and sometimes your columns are not, your structure is not straight. So this spacers will allow us to maintain a specific, gap in between the concrete and the liner, so that uniformly the grout is distributed uniformly. So this is one thing, and lastly I have about 7 minutes more. I'll take 1 or 2 more case studies. Sir? Thank you, sir. So this is the structure after we did the retrofitting of the piles, and it's almost been 4 years now, and we are still working on that for 2 more years, and none of the piles repaired have failed, or none of the structure which is repaired shows any sign of corrosion. Okay, I'll take up a case study of silo, wherein I'll show you some kind of instrumentation that we have done here also. So this was already tested and repaired once, but the root cause was very different. So what they did was, they saw some vertical cracks on the silo, and vertical cracks in a silo normally attribute to hoops, lack of hoops reinforcement. So what they thought was, crack in the concrete is because concrete kharab hai. So they started, repairing the concrete with epoxy mortar, and the cone also inside. A silo has inverted cone, so the beam of the cone also started settling, and that they filled up with plaster and some POP. And trust me, the load on that beam, that portion of cone was 14,000 tons of load. And I can show you the condition from inside. The cone started buckling, you can see, but luckily it didn't fail. So initially I thought it is a small void, so I put a pen inside, but that pen went inside, so I took a long wire, and the width of the beam was 360 mm, and wire went up to 360 mm, so it was through. You can see the void. So when we started extracting samples, you could see also plaster of Paris here. So एकदम बाहर से इतना अच्छा finishing कर दिया था, किसी को पता नहीं लगता अंदर क्या है, but it started settling, and that is when they realized that there is some problem. So what we did was, we started investigating. We did tomography here, and we realized that there were 40% void in the ring beam itself. 40% concrete was not there, and it's a compression member. You can just imagine how much already it had settled by 2.5 inches. Then for external surface, this kind of debonding, see, this is the repaired portion. They had repaired with epoxy mortar. You should never use epoxy mortar in this kind of repairs, because properties like coefficient of thermal expansion, creep, modulus of elasticity, drying, everything will differ from the original concrete. So don't use this in patches. So when we did GPR scan, we realized that the reinforcement which was provided in most critical zone was less than 20-30%, or some cases even more than 35%. Hoops reinforcement. So we did GPR, and these are the results of this is the storage portion, non-storage portion. So this is the apex of the cone, and this is the area where your pressure will be maximum. And you can see 23, 26%, 30%, 24%, all the deficiency were majorly in this zone. And as a result, those cracks were coming. And you can see all the repaired patches which were there, they had all turned hollow. They were sounding hollow. So it had debonded. And these are the results of the NDT and other things. So we are correlating all the three. And then what we did was, the plant that said they will not be able to take a shutdown. So you'll have to repair this in an ongoing plant. So we installed these gauges, these crack meters. So what will happen is, we installed this at 4 locations. And what we got was that, because silo loads and unloads at a rate of almost 250 tons per hour. So we wanted to make sure that while loading and unloading is happening, is there any kind of settlement or movement happening in that cone portion? Because otherwise during repair it may cause panic. So for a couple of months we started taking readings, and you can see up and down happening in the loading and unloading cycles. Then we started opening up these joints, put some additional reinforcement so that immediately when we open up the joints, the section won't cave in or collapse. Because we were operating at 40% of the total capacity, load capacity. 14,000 ka 40% were the permissible usage that we had given. And then we grouted by grout which had a particle size less than 0.5 mm, and we grouted by gravity. We did not use any kind of pumps. Reason why we selected gravity grout method was, normally what happens when you pump in some grout, there will be a sudden surge in the pressure, the level will go up, and as soon as you remove the port, there is a chance that it will settle. Second thing is, because grout has some water, when the water bleeds or goes off, the grout will shrink or it will settle. So what we did here was, we just took some pipes, we grouted that, we kept it for some time till it completely sets, and then we just cut the pipe, so that the entire section is properly grouted, and 100% we are sure that 100% cavity has filled up, because it's not a straight line. It may be some places it may be up also where we could not see also. And this is the line after the grouting was completed. After that we did tomography and other tests also. Externally we have proposed, or we repaired the structure by providing carbon laminates. Why not steel? Because when you use steel, steel has an elongation property, and silo is designed for a crack width of 0.2. So by the time the steel comes in action, silo will crack and collapse. Whereas carbon is not very ductile, so we use carbon plates for external strengthening of the silo, for the hoops reinforcement wherever it was short falling. Okay. So sir, I have 5 more minutes, sir. My time is just up. Perfect. So this is one more case study wherein we have done a steel stack repair. It is a 126 meter tall steel stack. External is completely RCC, internal is steel. So this was in 2018 we started this project. So initially there was no, the staircase inside this had collapsed. Steel section also had collapsed, and this is like ISMB 600. And the diameter of this is 4 meter, and internal platform supporting the steel stack also had collapsed. So we had no access to this, so we used drones to check the structure, and we found out that the concrete on the top portion was badly damaged. I'll tell you why it was damaged when we go through the presentation. The steel stack, some thickness at many places had reduced to even 1 or 2 mm, from almost 16 mm plate to 1 or 2 mm at some places. And it was, some places it had gone through. And this is sulfuric acid plant chimney. So it is, the fumes are highly dangerous. So this was the condition when we came in. Nothing was left inside. Platforms also had collapsed. And externally this was the condition. So we built a scaffold from inside, and externally we managed by suspended platform. You can see the condition of the steel stack inside. This was the level of corrosion that was there. At some places we tried even welding. Welding also, the sheet would tear. So then what we decided was, we'll strengthen this by giving carbon plates all around. Only in the portion where it was damaged. So carbon laminates cured in vinyl ester resin, because sulfuric acid epoxy cured laminates will not work here. It'll just go off. So we had used vinyl ester resin and grouts for all the entire repairs. The top portion was changed during the shutdown, annual shutdown. The staircases were replaced by SS304 staircase completely, top to bottom. Platforms were replaced by composite material. So we had used a lot of composite material, and all in vinyl ester resin, not epoxy or any other resin. And the top portion also was repaired with resin based mortar. Why the top portion was corroded? Because every time the chimney starts and stops, there is condensation happening at top, and sulfuric acid in concentration form is good. And if you reduce the, like if 98% sulfuric acid is better than 92 is like highly corrosive. So what happens is, whenever there is condensation, the acid gets diluted and that will damage the structure more. Even the wind cutters, which these are like 20 mm thick steel plate, 1.7 meter by 1.7 meter, part of it has already collapsed and part of it is already perforated. I mean, it was, so we replaced that with a composite completely wind cutters. And this is the structure before and after. So we took 3 years to repair this structure, with almost 2 years of non-working days. So because if there is any stoppage or leakage in the plant, you can't put your men, because if they breathe that, the person will die on the spot. So only in about 12.5 months we got working period. Rest was all lean period. So we could not put our men to work in that period. So this is how we reinstated this structure. Yeah. So thank you, sir, for that 5-minute extra. Oh, sorry. Okay, we'll not go to this. So I was also showing some case study of a collapsed bridge, wherein we did some scanning and things, and we could recreate the entire bridge if it was constructed, and found out what were the problems in that. So that is basically a thing which has to do with more of you can say BIM and those technology involved in that, scanning and BIM and all those technology. So that's the case study of that bridge which we had recreated. I'm not showing that right now. Maybe we have to keep something for next time as well. So thank you very much.